what is AI? Well, artificial intelligence is search. There's nothing else to it. And that might be a bit controversial, so maybe afterwards the AI experts can challenge me on this. But I think I will be always able to frame any AI program, any AI software to frame it and reduce it to search. So what is actually search? How does AI and search come together? Well, the easiest thing is to just describe it as an A puzzle. You could say, well, if my computer can solve an A puzzle, then it's an artificial intelligence because it can actually give it an A puzzle in a certain configuration. Remember, you played around with these, probably not played around with these, and as a child. So you have basically an initial configuration. You can move these tiles always a tile to an empty space, and you want to get from an initial configuration of the A puzzle to the goal configuration. And you try out a lot of things when you're actually playing this game. With time, you can become a little better at it. And I'm sure there are maybe real championships in this. So then we have the question: how is actually an AI now built for such a game, for such a puzzle? Well, it's just simply that we search the space of all possible moves that a person can make. So this is how AI then becomes a search problem. And what it does is we are drawing a graph, or a tree in this case actually, where we start with the initial configuration of our A puzzle, and then look at what moves can I make in order to bring it into the next configuration. So what I can do, for example, in the A puzzle, I can move this 5 tile up, in which case I'm in this configuration. I end up in this configuration. Or I can move this tile 1 to the right, in which case I'm in this configuration. Or the tile with number 2, I can move to the left, in which case I'm in this configuration. So now I'm actually having a tree that starts with an initial configuration, then has moves that I can take, and looks at all the moves. This brings me now into new configurations. And that can continue on until somewhere, actually in principle, this tree is infinite because there's always a move that you can make. So therefore, you'll get now. And what it is now to find a way to get from the initial configuration to the end configuration of your A puzzle, to your goal configuration. Well, that's just now finding your goal configuration somewhere in the tree, and then you know that any sequence of moves that led from the initial configuration to your goal configuration is now the solution to your A puzzle. And this is what the computer is going to do and present to you. So the computer will now present basically on the screen what it searched before. Now, that's a search tree, and there are different search methods that you can apply. I'm not going to show you just examples of 2, which we call the brute force search methods. So brute force means pretty much I'm the computer being completely stupid, knowing absolutely nothing about the A puzzle, for example, and just trying out all the possible moves in a certain order. So, for example, in breadth first search, the computer is searching this tree, and you can see the search almost like being in a maze and trying to find your way in the maze without having a map of that maze. So you're actually, one way to search the maze could be, well, I'm first going left a few steps, then I'm going right a few steps and see where I am. So you're building kind of a mental map of the maze while going through that maze. And that's pretty much what breadth first search would do. So you try first to look at what happens if I make move 1, that is possible, or what happens if I make move 2. So you have now the next part of the search is this one, and then you look at what happens if I make move 2. And then you say, okay, now if I haven't found my goal of goal configuration of the A puzzle yet, then I'm going to move a bit deeper and say, okay, now with 1 move I can't find the solution, that means let's try it with 2 moves. So now the next thing what the computer will do is try to go through all combinations of 2 moves in this tree, and then 3 moves later, and so on. So this is the search is going more into the brain. And then we can have the depth first search, where the computer says, okay, this is how maybe humans would go through a maze. They would start going into certain directions, move through the maze, move sometimes left, sometimes right, and sometimes at some point we'll stop and say, oh, I've been here before. And then maybe go back to where they started and then try something different. And this is a depth first search, where you first trying your first move, so your first step into the maze, and then continue on into the maze until you maybe end up at a dead end. So you're now in the maze, you're at a dead end. What would you do? Well, you go back to the last position where you had a choice in your maze, and you try something else. So and this something else could then bring you to another dead end. So at this point you backtrack again where you've been before, where you had a choice which you haven't taken before, and you look then at the next one. So the next node you're looking at is this one, and so on. So this is depth first search. There are certain problems with breadth first search and depth first search that I'm not going to go into. But in principle, you can see these are the kind of uninformed search methods that are brute force. I just try something and I really don't know where I'm going, what I'm doing. I don't have any idea of the maze that I'm in, but I'm just trying all the possible paths. So rather than doing that, in many domains you can't do that with computers, because in principle the search space or the size of the graph is just too big. And we are talking, for example, in terms of size. Sometimes the problems are as big as there are the number of atoms in the solar system. So we are talking about huge graphs, so we cannot search them really in a brute force fashion. So when AI researchers are faced now with this problem, they then fall back and say, okay, now we need actually humans to tell us what we are going to do. Namely, we need some heuristics. We need some kind of knowledge about the maze that we're searching, or some kind of knowledge about the problem we are trying to tackle with artificial intelligence in order to find a solution. So what is a heuristic? It's basically just some information that tells us which of the child nodes in our tree is going to be better to search first. So some kind of information, what looks better. When I'm in a maze, maybe I have an idea of the direction north, east, west, and south, and I know that somewhere the exit of the maze is somewhere in the north. So therefore I will probably try always to go north first and see whether I can get to the goal then, and only try the other directions afterwards. So this kind of heuristic is then used to speed up the search a lot, because now I'm not anymore blindly searching, but I have already an idea of which directions of search are more interesting, more useful. So in the 8 puzzle example, it could be which positions are better than other positions when I'm actually playing the 8 puzzle. It could be, well, the position where I have a fewer number of misplaced tiles, because this is kind of closer to actually where I want to get to in my 8 puzzle. Then another could be the number of moves required if no other tiles are in the way. Sometimes as a child, maybe you have taken actually your 8 puzzle, broken out all the tiles, and then brought them back into the configuration that you needed. So this is kind of measuring how many tiles you have to break off, and put back into your 8 puzzle in order to get to your goal configuration. So these are heuristics. And these are kind of heuristics that humans can give now to the computer, to the AI, and say, okay, look, AI, looks better than other positions, so try to make these moves first that get you into these positions than other moves. So you don't want to move somewhere where the number of misplaced tiles is bigger. Sometimes you might have to, but sometimes but in most cases it won't be a good thing. So heuristic search therefore finds the goal faster than the brute force search. But this is only as long as the heuristic is actually good, it's sensible. So these heuristics are sensible, but there could be other heuristics which get you into the completely wrong direction. So when you are in a maze and you're being told, oh, the goal is in the south, and you're always moving towards the south, but in reality the goal is in the north, then you're actually all constantly moving in the wrong direction. You'll probably not find the goal. So this heuristic is actually bad heuristic. So it's very much AI now at this point depends very much on the quality of the heuristic that the humans are giving to the computer in order to solve a problem. So you could say, well, this is very nice, now I can write an AI for 8 puzzles, but it's actually the case, and I'm happy to be challenged on this, is that any AI problem, any kind of task that you give to a computer can be reduced to search, and in the end becomes a search problem. So when we talk about the robot fetching beer from the fridge, which is clearly an AI problem that robot manufacturers are working on. Well, in this case, the robot is just searching through all possible actions that the robot can perform, and in order to find a sequence that leads to the beer being in the hands of the user. So we are actually here having a clear search problem. So it's not any kind of magical reasoning abilities that the computer has, employs, but in principle, the computer is searching. There are modifications to the search. You can frame it in a slightly different way. You can look at it, but in the end, it's really searching. Learning itself is also searching. So when we talk about computer learning, well, it's just searching through all possible generalizations of the experience. So there are many possible I experience something. I generalize from that in order to apply it better now to the next thing. So what the computer at that point does is searching through all possible generalizations of this experience that can be then reused in other tasks. And this is considered to be learning. So again, I have framed now learning as a search task. And what about storytelling now? How can we bring this idea of search back into storytelling? Well, we can see, for example, the search being the computer basically trying to tell a story at this point, searching through all possible story events. That means the nodes of my search tree are now the story states. This is basically what the story is at this point of time. So person A has been murdered. Character B is the detective who has now a suspect. Character C is the suspect who's running away. And all these, so this is the story state. And we have now this, we are searching this space of story states. Actually storytelling is a search through this space of story states. And the edges, which bring one state, move one state, transform one state into another story state, are just story events that move the story along. These could be actions by the characters, like the detective arresting someone. Or it could be just something external, like a building collapsing, and or a thunderstorm happening, and whatever. So all kinds of things that change the story state. And you can already see that maybe a lot of the art of storytelling on the computer, at least, is about defining what story states are and what these story events that move the story along are as well. So it's also a representation for computers. Another possibility is that the nodes are actually stories themselves. So you are now searching not the space of story states, but you're searching the space of stories. So each of the nodes in the search graph, in the search tree, are stories, and the edges that are how you tweak a story from one story to another story. So in one story, character A died, and the other story you make him live and continue. So you're actually changing the stories a little bit while keeping a lot of the story the same. So you're shifting maybe sometimes, making little changes to it. So again, you have though a search. You're searching through the space, and this is what AI will do ultimately. So story events here in this case is interpreted very broadly, because it's not. I don't say that it's very clearly defined either. So what is a story event? I think it's pretty much anything that changes the story state. So that means the state of information that we have about what is true in the story world and what is false in the story world. So a story event could also be a revelation. So it doesn't really change the state of the story world, but it changes about the information that we have about the story. Like watching a mystery, at some point you get to know, oh, he was the murderer. The butler was the murderer. So at this point now the story state didn't change. The butler was the murderer at the beginning of the story, the butler is the murderer at the end of the story, but my information of the story changed, so therefore I now am in a new kind of what I would call story state, and you're therefore having now a story event, this kind of revelation. So I'm interpreting it very broadly, and I'm sure that narrative theorists will argue with me about the terminology and that I'm using, but as I said, I'm coming from the engineering perspective, so trying to keep things a bit more simple. So, but overall, I now told you how interactive drama is framed, not just could, but is framed in terms of AI as search. And the question that I didn't answer yet, what is the goal? Because before in the 8 puzzle, I had a clear initial state. I have a clear goal state that I want to get to in the 8 puzzle by playing around, moving the tiles around. But in interactive storytelling, what is the goal? Or not even in non-interactive storytelling, but just storytelling. What is the goal? Where do I want to go in the end? I need to know what I'm searching for in order to make a successful search. If I don't even know what I'm searching for, I cannot search. I can maybe expand and tell you all the possibilities, all the story possibilities, but I don't know what I'm in the end am going to produce for the user. And this is probably where the main limitation of AI comes in, because the goal definition in interactive storytelling is not obvious at all. And I'm sure a lot of people have implicitly defined it, but explicitly getting there is still an open question. And in the end, what is the goal? It's to create a satisfying story, to create an entertaining story, to create an interesting story. But all these terms are quite useless for computers. The computer has no idea what interesting means, what satisfying means, and what engaging means. So what are overall now the components of the search? And these are the components that if I, as an AI researcher, want to tackle a task, and that includes storytelling, I want to tackle this task and create AIs that tell stories, then I need to first define the search space. That is, what is being searched. These are the nodes of the tree. I already gave you some examples, but these examples were very hand-wavy. I told you, well, let's call them story states. What is a story state really, and what are the important bits of a story state? Is it really all the little details, like which leaf fell from which tree in what way? Or is it more about the important events, like which character has been murdered and which character is the murderer and who is the detective and what is the detective doing? So that's might be initially maybe look like an obvious thing, but it really isn't, and it's a very subtle question. Search operators is the second thing. These represent the edges of the tree that are moving. That's where you move in your search from one point to another. So this is, for example, the story events that I mentioned, or the story tweaks. But again, these are not so far not clearly defined. It's not clear what is the best representation of these story events. If I have too many of them, my search space becomes very, very large, and there are too many possibilities that I'm looking at. So in some way, I'm trying maybe to restrict them. The third thing is the goal definition. I mentioned that already before. What are we searching for? What is an interesting story? If I'm searching for interesting stories, what is an interesting story? How can the computer recognize that a story that the computer generated is interesting? True. And another thing is that sometimes, even if I make a very smart definition of search space and search operators, then I still have a tree that is too large to be searched in a feasible fashion. Even though computers are very fast these days, they are only finitely fast. So there are problems that take a long time, especially when you have to search hundreds of millions, maybe billions of nodes. That means you can't do it in a reasonable amount of time. So in order to do that, then we might need the heuristics, which are kinds of the hints that tell us where to move during our search. And this is also something that we might need in storytelling, like, for example, which story action, if I move from one story event, I should say, which story event when I move from one story state to another story state, which is the better one to choose now at this point. And this could be just a heuristic, just a little bit of a hint from given by a user, given by a writer to say, look, these are better than these other ones in this state. But it's very hard to define it. But we will need it. We do need it in order to create the AI. Now, so far, what I've shown you is a search from a point of view of just a single AI searching, and there is nobody else who can interfere with it. However, once we have interactive AI, we have a user who can actually interfere with what and can shape the search space. So we might think that these are all the possible actions that the AI can do, and then this is the plan now that the AI has in order to solve the 8 puzzle. But if there is now a user, an interactive user, who's modifying the 8 puzzle on the way, then you suddenly, all the best plans fall together. So we need to have something which is an interactive search. And it is possible to frame and tweak our search algorithms to be able to deal with interactive search. And this is by having something which is called game trees. So it's again a tree structure that we're searching, where the nodes of the tree are states of the game or states of the story, if you're talking about interactive stories. And the edges are actions that get you from one state to another state. So here in this case, I just showed you tic-tac-toe, or noughts and crosses, depending on where you come from for this game. So here it's basically where you have, in this case, so you have on the first move, the player can put his cross in 9 possible positions. Afterwards, the other player can reply accordingly. For example, if the player moved the cross here, and now the other player can now interact and move the knot next to it, or the knot two squares away from it, or the knot below it, and so on and so on. And then we have, again, the first player who's placing the crosses, making a move, and so on. So we get now a tree, which is kind of this game tree, which we are now searching. And just saying one player makes a move, the other responds, and so on. You could actually generalize from that and say that the order of moves is not precisely specified. So we can actually expand over this, but in a simple form, this is now the space that we are searching. However, in order to search now, if I do the search and now create a path through this tree, I, as an AI who's interacting with the user, can certainly say, well, for me, this is the best path. But who tells me that the user is going to be the best path for the user? Because the user might think that this is a completely stupid path, he will just deviate from this path somewhere along the way, in which case all the planning that I did as an AI of the best path from the start position to the goal position might be void. So how can we actually get to the point where the search incorporates also what the user will do, and in some way tries to predict what the user will do?